to Calculus 2
and differential equations. All right, we'll see how that worked. So last time we started talking about differential equations, and I gave some definition and introductory story. I'm going to repeat some of that stuff now, and we're going to dig into some of the very basics of the whole thing. There are courses upon courses upon courses on differential equations, and we're just going to barely skim the surface. So differential equation is an equation which contains independent variable, function, and its derivatives. So the implicit form for differential equation, where you see x is independent variable and then function and then the first, second, and so on. The order of differential equation is determined by the highest order of derivative you have. So if there is a third derivative in the equation, you will say differential equation of the third order, and so on. So the solution for the differential equation is a function. You are used to equations so far, trigonometric, exponential, polynomial, whatever solution was always a number. For the first time, now you have the solution to be an entire function. And I gave you the example here. On the left-hand side, we are looking at the basic equation from algebra, where we subtract 3 on both sides, which is the opposite operation of adding 3. And we get x equals 2, and I show the graphic approach to solve that by graphing the left and the right-hand side of the equation, looking at their intersection. On the right-hand side, in black, dy over dx is equal to x cubed plus 2. That was differential equation, and because differential equation had the derivative, the integral is the opposite operator. Therefore, we integrate both sides, and we get the solution of, once we integrate, of x to the 4 over 4 plus 2x plus c. And this is where you see that the solution is a function, not a number. So it's a higher order creature, right? Completely new concept so far, and it opens doors to, as I mentioned, many courses, many courses after this on differential equations, dynamical systems, and partial differential equation. So years and years of stuff if you are interested in this. Now, I also told you that all of our engineering, physics, chemistry, everything is governed by these equations, because all of the formulas that you have in these areas are all derived from a differential equations. Every formula is a solution to the differential equation. And I started that talk by giving you the most basic idea, where I said that the change of population in time is proportional to population, which means that if you have more people, it's going to be easier to get more babies around. If you have less people, you're going to have less babies coming around. So the largest populations on the planet will be able to grow faster, and the smaller populations will grow at a slower rate. So that is captured in this equation. The change in population, that's the derivative of population, and then is proportional, that equals k times the population p. And now I used what is known as the separation of variables, which is the most basic technique of solving differential equations, where you put the same variables, in this case population, on one side, and then time variable, independent variable, on the other side, and then integrate both sides. The integral of dp over p is ln p. On the other side, since the main variable is time t, you get kt plus c. To fish out p, we e both sides and follow some algebra to come up with the model. Now, you've seen this model in your pre-calculus course. It was just given to you. But now you see where it came from. Now, to work more on these concepts, we are going to take a look at physics. We learned that acceleration we know it as the change of velocity. So I will say that acceleration is the change of velocity in time. And let's say you have that as negative g, right? So just we are considering gravity to be acceleration. So we're talking about a free fall of the object. The negative sign denotes that the object is falling down while the y-axis is pushing up, right? So now if you look at this, we know that g is constant, so we don't have to worry about that. That's not a variable, right? But velocity is a variable and time is a variable. So separate vars, separate variables, we are going to get to a point where we have that dv is equal to negative g dt. And at this point we integrate both sides. What we get is that v is equal to negative gt plus some constant c. Now I'm going to call that constant c initial velocity, because if you observe equation carefully, for t equals 0, which is initial state, right? T is the beginning of time. So when t is equal to 0, your v is equal to c. So you see that c is the velocity at the beginning of time, right? So that's why we can immediately call c initial velocity, and we can write that v of t is equal to v0 minus gt. Now, some of you might recognize, depending on how much physics you learned so far, you probably know equation velocity final is equal to velocity initial plus acceleration times time. That's that equation for free fall. You can see it, right? Depending on which way you learn it. Maybe you learn it with v final minus v initial is equal to acceleration. I'm not sure which way you've seen this in your physics class, but that's it for the free fall, where acceleration is gravity, and it's negative g because it's going down. Now, I'm going to push this forward and say that velocity is change in acceleration. And velocity being, velocity is a change in position. Change in position. So I'm going to write velocity as change ds over dt. Negative gt plus v0. And I see that s is a variable that depends on time. And we have dt. So again, I'm going to separate variables, and I'm going to get to ds is equal to negative gt plus v0 all times dt. So we see that we know that g and v0 are constants. T is the variable, so we have all of the t variables on the right and all of the s variables on the left. Now that we separated variables, hit both sides with the integral, and you get that your position s as a function of time is negative 1/2 gt squared plus v0t plus some constant c, and we'll call this c initial height for the free fall, which is s0. And you should be recognizing this formula from your physics course as well. Do we remember the parabolic motion formula? That's the one. So this is another demonstration of how you derive formulas in physics. You look at the concept as a sentence of what you observed in nature, and then you transform that into differential equation, and then you just grind through mathematics, so solving differential equation. Now, in the beginning, all of these formulas are simple, and all of these formulas are about 400 years old, right? The newer stuff follows much more complicated mathematics and really crazy differential equations. that usually are solved numerically or some other way, because they're extremely difficult. But most of the physics can be derived using these methods. So we get to the point where we work on classification, and I already said that we understand what the differential equation is. I already said how to classify differential equations using the order. So order is the highest derivative. And then we have the linear versus nonlinear differential equation. Now, a linear differential equation is the one where the function is not squared or embedded in sine or e or anything like that. So if I say, let's say f prime, well, let me use y prime. So y prime plus y is equal to sine x. This is a linear differential equation. And then if you have y prime squared minus 3y is equal to sine x, this one is nonlinear. You see that there was a y prime squared. You might have, let's say, e to the y minus 2x equal to y prime plus 3. That's not linear either, because e to the y, right? If it was e to the x, it would be linear. So you are not allowed to have any kind of function composition with y's. You can't square them, can't cube them, can't put them in sines, cosines, tangents, nothing. So we have the world of linear differential equations and world of nonlinear differential equations. So that's classification. Another classification is homogeneous and non-homogeneous. That means equal to a function which is known as the forcing term, or equal to 0, which is steady state. There are many other classifications that are out there, most of which you will see obviously when you take differential equations class, which is the class you can take after Calc 2 right away. I would recommend Calc 3 first, because two things that you will need in differential equations are covered in Calc 3, mainly partial derivatives and procedure, which in Calc 3 is known as potential function, and in differential equation known as exact equations. So there are certain things that Calc 3 will be very beneficial for you guys to, and if you're a computer science major, just don't worry about any of the two courses. Make sure you have linear algebra and discrete mathematics, both of those courses done if you are a computer science major. But if you're mechanical, electrical engineer, civil, all of this kind of stuff, so non-computer, make sure Calc 3, differential equations, and linear algebra are all on the pile. Linear and discrete. Your major will ask you to pick one of the two, but you will be severely disadvantaged if you skip any of the two, because one deals with algorithms, which is programming in general. The other deals with matrices, which is higher end programming like arrays, but you're talking about search engines and compression files like MP3, JPEG, and so on. So you learn that through linear algebra, and you learn the algorithms of the code and stuff through discrete. So you really need both courses.
Is that like kind of modern type math now?
What happened?
And you said all the math is really all, but is that modern today?
No, that's the basic stuff that we teach here at RV. But the computer programmers, computer science program here at RV says one or the other. But you really need to take both. That's the scoop. All right. So that's what I have on classification. So now I am going to put the formula down for the first order, and I'm going to put this in red. First order linear differential equation. This is my abbreviation DiffEq for differential equation, and that one will be given as y prime of x plus some function p of x times y of x is equal to f of x on the other side. So this is the first order linear differential equation, and we can come up with pretty much any example of this. So y prime minus sine x times y is equal to x cubed, whatever. So that will be the example. Now, you will learn a whole spiel of methods in differential equation class how to solve this. In this class, we are only concerned with separation of variables as the most rudimentary and basic technique. When you go and do the other stuff, you are going to learn the method of undetermined coefficients, the method of variation of parameters, the exact equations, and all of these other cool things that you can do to solve these equations. We are going to be concerned over here with very basic equations as suggested by the author. So the first order linear equation with constant coefficients. So no p of x, it's going to be a constant number there. So I had sine x in my example. It's not going to be sine x, it's going to be maybe 3, all right, or something like that. So we are looking now at the first order linear differential equation with constant coefficients. So what I'm going to do is, well, the equation is y prime of t, let's say t is the variable, is ky, obviously, of t, plus b. So k and b are constants. They're not functions. Solution is y of t is equal to ce to kt minus b over k. Now, you might be tempted to memorize this, but every single problem in there can be solved by separation of variables. So you don't really have to memorize this, but you can. So I'm going to work on example. I'm just going to make up y prime is equal to 3y minus 8. All right. So I'm going to solve this by separation of variables. First, I'm going to use Leibniz notation. Oh, by the way, you can just pick off k and b, plug them in the equation above, and you're done, right? Because this is the solution, and if you just pick k and b, which is obviously 3 and negative 8, and plug them where they belong, you're done, right? That's if you memorize the equation. But what I want to do is I want to solve it. So dy dt, Leibniz notation, and I do separation of variables. Now, because of minus 8, I have to bring the entire thing with me. We hit the integral on both sides. We know that on the first one we are getting the ln, right? So we're going to have ln of 3y minus 8, and we need 1/3 in front because of the u sub that we're supposed to have. And on the right hand side we have t plus c. We are going to multiply both sides by 3 to get ln alone. And I'm going to have 3t. Observe that I'm not writing 3c, because c is the constant that absorbs times 3. So there's no need to write 3c. We can just write c. So now we are going to e both sides, and that will free 3y minus 8. On the other side, we are going to have e to the 3t plus c. Now, I already told you the rule here. If you remember from your algebra, that if you have addition and subtraction in the exponent, it's multiplication of, right, or division of bases. So we have 3y minus 8 is equal to e to the 3t times e to the c, and you can call all of this again c, because it keeps being a constant. It doesn't matter. So now I am at the step that looks like this. Plus 8 divide by 3. Again, divide by 3 gets absorbed by c, and that will be solution. Yeah. U sub. If I'm integrating this, u is equal to 3y minus 8, du is equal to 3 dy. I don't have a 3, so I will put 3 and I'll put 1/3 in front. Now my favorite part is check. As a student, I always loved integration because it was easy to check. You take the derivative of what you get, and if you don't get what you started from, it's wrong. It's very simple. So now we have what y is equal to. We also have the differential equation. I have differential equation which is y prime 3y minus 8 equals 3y minus 8. All I need to do is to plug in, and if the equation works, it's correct. You know how when you solve x plus 3 equals 5 minus 3x equals 2, and then if you cared, you check 2 plus 3 is 5, 5 equals 5, we're good, right? You are doing exactly the same thing, except now you get to plug in functions, not numbers. So clearly I have to plug in the derivative, which means differentiate this thing, and then plug in the solution, which is y. All right, so what's the derivative of y? It's going to be 3c e to the 3t plus 0. Great. So now plug everything in. Equals to 3 times y, which is ce 3t plus 8 over 3, and then minus 8. So if this works, if it checks out, we're good. On the left hand side, I have 3ce 3t equals to, distribute 3 now, 3ce 3t plus 3 and 3 will cancel, and then these 8's die, and left equals right. Do you see that?
No. I don't think we are. Yeah. I always wonder how you made them both equal to each other.
No, I plugged in. I took the derivative of y prime, that's this, equal to 3, that's y, times 8.
Okay.
So I plug this y for y, and this is the derivative of that.
How were you able to get rid of 3?
I multiply. So 3c, and then 3 times 8 thirds, 3 and 3 will cancel, to get plus 8, and then you have minus 8.
Okay.
And they cancel. So once you solve differential equation, you can always take the derivative and plug it back in. If you get the solution to check out like this, that means that your solution is correct, and you move along with your life. Now, as I said before, differential equation, highly applicable course. It's applied mathematics. So it says initial value problem for drug dosing. A drug is administered to a patient through an intravenous line, whatever, at the rate of 6 milligrams per hour. The drug has a half-life corresponds to the rate of 0.03 per hour, and let y of t be the amount of drug in the blood. For t larger than 0, solve the following initial value problem. All right. So now what we have is that the change of the amount of drug in a system is equal to the half-life times the amount of drug plus 6, which is the rate at which the drug is coming into the system. This is the differential equation we just solved. It just has numbers to it, has meaning to it. So you have a rate, a rate, a rate. They're all rates. So we can just write the solution because we know what the problem is. Oh, I already have it in mind. So this works out to be CE negative 0.03 T 200, right?
Plus the double negative, because it's minus P divided by K, or K is...
Oh, yes. Plus 200, good. Now, what I have is the initial condition. This is new. Pay attention. Initial condition says that y of 0 equals 0. This means that at the beginning of time, t equals 0, there was 0 drug in the system. Right? So I can use that with my equation. I'll write the equation one more time. To determine C. Because I know y is equal to 0. CE to the negative 0.03 times 0 plus 200. So what I get is that 0 equals C times e to the 0 is 1 plus 200. We get that C is equal to negative 200. So what is the solution? Y of t is equal to negative 200 e negative 0.03 t plus 200. What happened? Oh, come on. Yeah, if it's...
Oh, man, it got me mad.
Now observe what's happening here. When t is equal to 0, you get e to the 0 is 1, minus 200 plus 200 cancels out, 0 drug in the system. Let the t go forward in hours. T equals to 1, we get how much drug? T equals to 2, we get how much drug? Right?
Or 500.
500 hours? How many days is that? 48 in 2. Right? Let's not take that much.
About 21.
So I would like you to try some of these, and then we'll talk about the slope field. What happened? That one looks done. Well, I'll pick a few of this one. So basic skills first, meaning verifying solution. All right, your job is to plug into differential equation and check if it's correct. So let's start with problem 10. Here is your differential equation. It says ty prime plus 3y equal to 0. And the solution given is y equals ct to the minus 3. Here, c over t cubed. Check if this solution is correct. And we'll do one more annoying than this when you're done with this. Yes? What happened? Plug in. Get the derivative of y and plug y prime.
Y prime equals the equation.
You'll find y prime on the side first.
Oh, it did.
Okay, so now plug it there and plug y and work out the algebra.
May I show you what I'm doing so far?
This is like if you equation and say x equals 3 with solution check. You just need to plug in to check. Bye.
I'll be back.
I'll be Mozart. Got it? Plus 1 or minus 1 rule, depending on whether it's integral or the So what's y prime?
Negative 3y divided by 3.
Yes.
What happened?
Negative 3y divided by 2.
Negative 3y. Negative 3c by t to the 4th. You're taking the derivative. This was c t to the minus 3. You copy the constant c times negative 3 t to the negative 4. Derivative. You take the basic derivative. And now you just plug this there, plug this there, and make sure they all work out to be 0. So t times negative 3c over t to the fourth plus 3 times c over t cubed equal to 0. T and t cancel. I get negative 3c over t cubed plus 3c over t cubed. 0 equals 0. Good. Solution. So we're just plugging in. Now, what happened here? What happened here? This is what happened. You have x plus 3 equals 5, and I gave you a solution x equals 2. You plugging in 2 and making sure it's 5. That's all it is, except it's with functions. So, more algebra and more work. So you have the differential equation and you have solution given. You are not solving anything. You are just making sure it works. So,
Is that a separable differential equation?
oh, how to solve it?
Yeah.
All right, let's check. So we have t times dy. The question is if it's separable. Plus 3y equals 0. I'm going to move 3y first. And then I'm going to move t and dt and move 3y. Yes, it is. It was separable. Separable differential equations will be very rare when you take differential equation class, right? It's going to be very rare. So over here it worked. And you can solve this to figure out if these are going to give you solutions, right, that you desire. So the first one is negative 1/3 ln of y is equal to ln of t plus c. So as you can see, I'm solving it now, but it worked out to be separable, so it's not a big deal. This 1/3 jumps inside the ln. And we get this. E both sides. Over here we lose this. Now on the other side, we get ln and e cancel. We just get t times e to the c. Call it capital K. And now, what I'm going to do is I'm going to say this becomes 1 over cube root of y, kt on the other side. Cube both sides first to get rid of the cube root. Your goal is to get y alone. And then this k becomes, again, k t cubed. And now flip both sides as a fraction. And call this 1 over k c, whatever. And there you go. So it was a separable equation. You follow calculations and so on. Again, for you guys, you're just seeing this for the first time, so it seems complicated, but this is the cheapest possible method. It's rare. It's almost like u sub or, you know, more rudimentary than that, actually. All right, let's take a look at the more calculation intensive. Again, you are not solving, I'm giving you solution. Your job is to check it, which means plug in and check. So this is problem 11. Your differential equation is second derivative y plus 16y is 0. Solution is y equals c1 sine 4t plus c2 cosine 4t.
What do we do to C1, C2?
Those are constants, just drag them around.
Okay.
I know. What was that? Yeah, I don't, but I'll try, I guess. So, the first time I've seen these problems. Obviously, this is the first day of your differential equations class. Immediately reminded me of the basic algebra. This is how I associate things, right? So in basic algebra, you had a problem that looked like this. Let's say 3xy minus y squared when x is 6 and y is -2. Right? And then you were supposed to plug stuff in. So you will get 3 times 6 times -2 minus -2 squared. So, and then you compute and you find the number. Now you are doing the same thing except you're doing it with functions. You don't get 6 and -2 now. You get, right, as x and a y, you get y double prime and y to plug things there. Now, I'm not sure why it says y1 over here. It's just y. So now I need second derivative to plug in, and y I already have. So I have to go find the second derivative. Y prime is, c is a constant, we copy that. 4 comes out as a chain rule. So 4c1 cosine 4t, derivative cosine is negative sign, so minus 4c2 sine 4t. Second derivative, another 4 comes out, so minus 16c1 sine 4t, and then minus 16c2 cosine 4t. So what I did is I took two derivatives because I need to plug in second derivative. It was a second order equation. So now this thing goes here and this thing goes there. Plug in. So -16 c1 sine 4t minus 16c2 cosine 4t plus 16 times c1 sine 4t plus c2 cosine 4t. Is that equal to 0? Right? Because it's supposed to equal to 0. Well, you see negative 16c1, positive 16c1, so they do actually all cancel, and we get 0 equals 0.
So when they're multiplying, the 16s don't get absorbed by the c's?
You can. It's just going to be c1, c2, c1, c2. Problems 17 through 20 are called warm-up initial value problems. And let's take a look at 18. It says dy dt is equal to 8e negative 4t with the initial condition y of 0 is 5. So you need to solve this now, right? Solution is not given to you. When you solve it, you will get that c, and you can calculate the value of c using initial condition. So go on, solve this.
equals negative 2. Yes, with the x value. We get negative 2. Yes.
Differential equation 3a.
Okay, we did do calculation with plus like trying to solve C and all and calculus ones. Didn't we? We did calculation with one column for C and calculus 1.
Yeah, for indefinite integral, we find plus the same thing. That's it.
So you know how to do it. When you see initial condition, you can find C. For the second order differential equations, you will have two of those guys, and you can find C1 and C2. Because you've seen the previous problem, for the second order, you had two C's, right? And that will come up, they will be coupled with two initial conditions, and you will be able to find both C's.
How can we find them so they easily? It's something very hard because one of them, and then trying to solve one, you have to like plug in for 0 when you're trying to solve for x or trying to solve for
Well,
y.
for these guys, depending on which way they're given, you might find one by one, or you will have to do the system of equations, depending on which way it's given to you. You have a headache from this stuff? Oh man! You should have taken some coffee. Apparently, it works. We use separation of variables, right? It doesn't work. So dy is equal to, kick 8 out, right? We'll have these integrals, 8 minus 4t dt. We're going to do separation of variables, and then we have on this side just y equals 8. This is e minus 4t divided by negative 4 plus c. These guys now cancel. And this is where initial condition comes in. You are plugging in y equals 5 for t equals 0, right? So that's 5 is equal to negative 2e to the 0 plus c, from where c is 7. And then we move on to the next one. Right? Done. Of course, it's math. Here are the spicier versions. So these are the first order linear constant coefficients, and you either memorize the formula and you use it, or use separation of variables and then do the whole procedure. Up to you. I really don't care one way or another. Problem 26 dy dx is equal to negative y plus 2. Y of 0 equals 2. Now, I did solve this problem before, so if you get stuck, look up 3 examples ago. Actually, different numbers, same problem. After this example. And then that's it. Then we'll do a little bit of the review of the list. Unless you're in rush.
I know we kind of dealt with that y equals q c of e to the 3x minus 4, however that formula is. It said y equals c of e kt and times b over something. Okay. So I'm wondering if those are type of problems that we're going to deal with inside the bonus column or on and would that be how can I identify when I need to use it?
Just like when you know when you use integrations by parts or the tree sum, right? You identify where it is. So minus 0 equals to
We solve it like the what? We solve it.
you can do the procedure or we can memorize the equation.
Yeah, what if I want to say like this? So I got y equals and y equals
I don't know. Let's see. No, that makes sense. But the trick is that I learned this stuff because it's interesting and beautiful and I like it.
Why you said the type of stuff to do with the point that here and all I know it is.
Well, in certain cases you have to use it. Maybe we have computers to take care of it. When they did the Manhattan project, they had a unique graduate student computing the very biggest calculations they can because they were computers. They had some graduate students, mathematics, they were calculating. The lead scientists were coming up with concepts. So computers can calculate complicated calculations. And at that time, that was today you have the computers that, you know, the cell phone has the entire TI-84 calculator on it, right? Look at it. All right? So the entire power of this calculator is on the cell phone, right? So the whole thing is you have access to insane computing power there. So that's why you don't really need that by the time you know what it is because you can plug
Also having a problem with both macros, so it's important to find out knowing that all it is, but trying to split from it.
you have to call this.
Also, I have a TI inspire. I just want to say I did have it before, but I couldn't find a charger for it because battery died. So I found a battery that fits it, and I turned it up. Yeah, USB. Like yeah, that's what I did. Yep. Yeah. Yeah. After we have breaking points now.
We have one more concept and then eventually. All right, let's take a look at this. So, did you get to calculate C at the end? Great. Let's do it. We all good?
Seeing sounds.
All right. So we hit both sides with the integral, we get ln of negative y, you know what, 2 minus y, the hell. And then we have a negative 1 in front because the u sub, right, equals to x plus c. And then this negative 1 will make it ln of 1 over 2 minus y equals to x plus c. And then we and then 1 over 2 minus y is equal to just c e to the x when you go through transformation. Flip both sides, so we have 2 minus y is equal to c over e to the x. So you swap left, you swap right, that's where you pick up, the x goes in the denominator. 1 over c is still c, that's all constant, no one cares. Move things around, right? So you should have this at some point in life. With initial condition, that's a negative 2 right there. So it's also a negative 2. Oh, you're using pen? Ah, too bad. Yeah, it's a negative 2 in the textbook. I'm working on a problem 26, so it's a negative 2.
Professor, how'd you get the negative from the c over e to the x?
Like this, right? Because y goes this side, becomes positive, this guy goes this side, becomes negative, and 2 stays where it is, and I swap the sides at the same time.
So if you just memorize like the formula, then how does that work? You'd have
I don't know, I don't like to memorize, so you'll figure it out. Don't forget that your k is negative 1, right? E to the 0 is 1. So C is 4, right? Is it? Bueno. One more concept and we're done with the lecture. Yes?
Basically what I did was dy dx. I said dy equals c with y plus by 2 dx. And when I did the integration, it got a1/2y.
You can't have the y's and t's on the same side. You have to move all the y's on the one side.
I know I said you have to do all the y's on one side. But what will the plus 2 when the 2 stay on that one side because of the constant?
Yeah, you can have 2 on either side. It doesn't matter. It was just convenient for me to do it that way. So we can take a look again at this. One more concept, and then we're done. What happened? Do I have to? Where is your soul, man? Y prime is equal to negative y plus 2, right? And we have y of 0 is equal to negative 2. The formula was y prime is equal to ky plus b, right? So from this one, we find that k is negative 1 and b is 2. The solution to the differential equation was y equals ce to the kt minus b over k. So y is equal to ce, k is negative 1, so negative x, minus and minus give me a plus, and then I have a 2 right there. There it is. Right? That's it. Happy? Good. One more concept called directional fields. I need you to focus here. Focus. Directional fields are a way to solve the first order differential equations graphically. And then you look at the shape of the functions you get, and you guess the solution from there. I already told you that you can solve regular equations, basic equations, using graphical method. You graph equation on the left, you graph equation on the right, and wherever they intersect, x equals a number is the solution. If you have multiple functions, they will have maybe 2 solutions, maybe 3 solutions. Maybe if you intersect sine with a linear line, you get infinitely many solutions. You can have any of those combinations. Well, now, directional field, also known as a slope field, is a field that it's filled with these small line segments that force the solutions to flow through them. It's like little guides. Now, you've probably seen a lot of those if you read the book and did the class prep. And I'm going to show this in a textbook first. Going to use the marker here. So what you see is on the upper graph, you see the flow, and you see how these lines have to follow the guide. So I can come in here with another one and then follow like that, follow like that, like that, like that, right? Do we all see that? It has to follow the guidelines. So now, looking at the problem over here, you see how it comes in from here, it straightens up, and then follows and falls in here. Do we see that kind of motion? Stuff coming in from the top as well. There are infinitely many of these lines that are all doing the same thing. Infinitely many of them. Only with the initial condition, which is the point somewhere in this region, you get to single solution out of infinitely many. The plus C part, or C, whatever is incorporated in the solution, is the one that gives you infinitely many lines. As soon as you put the point, that point has to be somewhere, and only one line can go through that point. And then it becomes what we call particular solution. I haven't used those words yet. You have a general solution, which is with a C in it, and you have a particular solution. That solution is when you have initial condition, and then you find value of C, and that is the function solution. So in this case, something like this goes through that point and goes where it needs to. So how do we draw directional field? Because that is what we need to do. Differential equation makes the field, and then solutions navigate through that field. So we are going to learn now how to come up with this. And Calc 3, same stuff, right? We are going to have the field there as well. So say dy, let's do dy dt is equal to x plus y, say, I don't know, whatever. So pay attention how I do this. It's very systematic. We know that this part over here is the slope of the line, of the tangent line. So what I'm going to do is I'm going to set that slope to be, say, 0. So if I use dy dt, this better be ty graph. So I'm setting slope to be 0. When I plug that in, I get 0 is equal to x plus y, from where I'm solving that y is negative x. So I'm getting this pair over here, where I have the line y equals negative x, which is called the isocline, and I'm graphing that line lightly So this is my line y equals negative x. Along that line, I am going to put these little slopes that are the little black lines, and observe that I put them all horizontal because the slope is 0. Then I move on and I pick m to be 1, which means that dy dx, right, is 1. Dt, sorry. So that's 1 is equal to x plus y, from where y is equal to negative x plus 1. So I have this pair now. I graph my new line, isocline, and I put slope 1 all over it. So my new line is going through 1. And the slope on it is 1, which means like that. Because that's the 45-degree slope. It's a very tedious work. Now we pick m equals 2, 3, 4, negative 1, negative 2, negative 3. Graph them all. That will fill the entire space with the little lines, and then you get to snake through the solution. It takes time. Takes time. And builds character along the way too. No yawning. Problem? Good. So m equals to 2, which means dy dt is 2, which means that 2 is equal to x plus y, which means y is equal to minus x plus 2. There we go. So now we have the isocline. That is going through 2. At 45 degrees. And now our slope is 2, which means it's more slanted than before. That's okay. You can get it over the allergy, just like a peanut one. Just eat a lot. Yeah. M equals -1. So we have negative x minus 1. Isocline. And then the slope was -1, which means 45 degrees this way. No, wait, that's positive 1. Oops.
Would that be parallel to the line?
Yep. Now I'm getting there. M equals -2, right? Because dy dt was -2. That's -2 equals to x plus y, so y is equal to -x minus 2. Isocline. The first rule of engineering, draw big. Unlike me over here. Slope is -2. That's going to be slanted more, going down.
I may ask you for name, why how is it parallel to the line?
Because the slope of the isocline was -1 and each slope was -1. So they were both the same slopes.
Okay.
So without drawing 5,000 of these,
Character question. If it was y equals -2x, would it be would it then be parallel to the line then?
yeah, because they have the same slope.
Okay.
So without drawing 5,000 of these, the general solutions must do this. That's how they're going to look like once you complete the field. Because the further away you are from this -1 isocline, they're going to curve more because the slope goes 1, 2, 3, 4, 5, 6, and they all go towards being vertical.
Yeah, I just go the direction isn't going to be
That's how the flow is. Look. See? Whatever you throw in here, it's going to fall this way and shoot out, right?
Yep.
Drop it in this slot. Drop it into this slot. See that?
Yep.
So think of it that way if you want to. Like drop a penny and like, woo! On a test? This is too much. Take 45 minutes to draw this. I said, well, actually, if we go to test, you put this problem in another 2. But it's a really cool thing because you actually are not doing any integration, not doing anything. You are assigning numbers and slopes, and then it's just tedious. There's always a trade-off, right? Remember the approximation, right? You said tedious trade-off, right? Yeah. For 7.7, whatever it was, right? Simpsons and Simpson trapezoid. So you are doing middle school math because you're just computing the function, so it's easy. But right, you have to do a lot, so it's a trade-off. It's as I would say, right? I learned the expression in US. There's never a free lunch, right? What's up?
What are some of the applications of this that you think off the top of your head just having graph representation? I mean, I know it's
Signals,
like,
like this, right? That's technically a lot of stuff later on. You would rather look at the graph than actually calculate stuff, especially in engineering. You don't know how to read graphs, you're just done.
So this is why I have to ask. This is why equals negative x. I thought x equals negative 1, but it's that y is the same thing, negative x is the same thing.
That's why they are talking. All right, guys, so that's it for differential equations. I know there is much more, but then you will enjoy, differential equations later on. And here's the same stuff in DFQ class, day 2. So you'll have much more of these cool things, separable, except a little bit more interesting examples of separation. And you'll have a whole bunch of other cool stuff to do. So, stream sounds. Let's just say bye, stream.